Hello and welcome to this tutorial about Merkle Trees. So Merkle Trees are a simple but effective data structure in driving blockchain technology such as Bitcoin. So without further ado, let's dive in. So there is one prerequisite that you need before embarking on this tutorial, and that is you need to have a basic rudimentary knowledge of what hashing is and what it does. So if you know what hashing is, you're good to go. Now let's go back to the basics. What is a blockchain? So if you notice, a blockchain is made up of two words, block and chain. And as one would have guessed, a blockchain is essentially a chain of blocks, a bunch of blocks that is linked together. So now let's zoom in into one block and let's look at what one block is made up of. So there's quite a fair bit of information, so let's take it slow and take a look at each information one at a time. So the first that we see is a nonce, which is a random number that helps facilitate the proof of work consensus mechanism that is common in blockchain technology such as Bitcoin. It also contains the hash of the previous block, which actually helps safeguard the integrity of the blockchain. Now, you might be asking, how does the hash of the previous block safeguard the integrity of the blockchain? This is because this actually prevents malicious attackers from overwriting past historical transactions of the blockchain, since everything is linked together. Lastly, we can see that we have the Merkle root. So the Merkle root is the centerpiece of this video. It is the star of our show, and I'll be talking more about the Merkle root later on in this video. So lastly, we have a list of the hash of transaction. We have a hash of transaction 1, hash of transaction 2, hash of transaction 3, all the way up to the 500th transaction. Okay, so this is essentially just a list of the hash of transactions that has been done at one point in time. Now, one thing I just want to add is that the first three information in the block, the nonce, the hash of the previous block, and the Merkle root are part of what we call the block header. Now, of course, this is a simplified version for tutorial purposes. There's actually much more metadata in the header, such as the timestamp of the block, such as the difficulty target of the block. So if you're interested, feel free to go and read up more online. Now, let's take a look at this scenario where January is the verifier. So January have just sent money over to header, and now he's inquiring as to whether his transaction is confirmed on the blockchain network. He wants to inquire whether the process of subtracting the coins from his balance and the addition of coins to header's balance is actually verified and committed to the blockchain network. Now, there's only one way to verify whether his transaction actually followed through, and that is by asking a blockchain node. And let's call this blockchain node Flip. Now, what is a blockchain node? A blockchain node is simply a computer that stores the entire blockchain since time immemorial. So basically, in other words, it stores the list of transactions all the way up to the very first transaction. So now, imagine if Flip, the blockchain node, replies with this response: hey, your transaction ID blah 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 is on the blockchain. Now obviously, if we were to receive a response like this, we won't be satisfied. How do I know that Flip is an honest player? How do I know if Flip is an honest node? How do I know if Flip is not lying to me? What if the transaction has not followed through at all and Flip is just lying to me? There's no way of knowing, right? And let's say if January wants to verify and physically inspect the whole blockchain himself to see for himself that his transaction actually followed through. And the big idea underlining blockchain is that it is a trustless and permissionless system. So essentially, a blockchain is a system that functions without trust. It should be able to function when nobody is able to trust one another. This also means that everything must be openly auditable and verifiable. So in this case, in this context, nobody should be able to stop Jeremy from physically inspecting the blockchain himself, especially since blockchain is a trustless system. It's a system that's not built on trust, meaning he doesn't have to trust Flip at all for this to work. So this means that Jeremy will need to download the whole block in order to verify his transaction. But this is a waste of computing resources and time. Because the thing is, he doesn't need to download the whole block. So as you can see from the previous slide, so let's say this particular block contains 500 transactions. The thing is, Jeremy doesn't need to download all 500 transactions. This is a waste of resources as said earlier. Also, the time and space complexity of this is linear, ON. Okay? So there's actually a method to overcome this certain limitation, and this is with a certain data structure called Merkle Trees. See? So Merkle Trees are a simple but powerful data structure capable of accelerating the time and space complexity to logarithmic O log n, okay, which is a huge improvement. And you will see how later. Now, with Merkle Trees, Flip simply needs to give Jeremy the Merkle root and some selected nodes in the Merkle tree. Again, I'll explain what are these selected nodes later on. Now, let's take a look at a visual representation of what a Merkle tree is. Over here, where my mouse is hovering around, is block 1. And block 1 contains the hash of transaction 1. Block 2 contains the hash of transaction 2. Block 3 contains the hash of the third transaction. And all the way up to transaction 10. Now, transaction block 1, 2 contains the combined hash of transaction 1 and transaction 2. Block 3, 4 contains the combined hash of transaction 3 and transaction 4. Block 1, 2, 3, 4 contains the combined hash of transaction 1, 2, 3, 4. This particular block, as you might have guessed, contains the combined hash of the first transaction all the way up to the 8th transaction. Okay, so I think by now you should have a rough idea of what a Merkle tree contains. So now let's move on. One thing I want to highlight is that the topmost node in the Merkle tree is known as the Merkle root. And this Merkle root, which is the combined hash of all these transactions, is the exact same value as the Merkle root in the block header. It's the exact same value. Now, let's go back to the scenario with Flip and Jeremy. So again, we are faced with the same scenario, just that the transaction ID has changed to make it a little bit more concise, to make it a little bit more explainable. So basically what this is saying is, it's basically a shortcut to say Jeremy's transaction ID is the hash of the third transaction. Now let's say Flip, which is the blockchain node, replies with this response. He gives Jeremy the Merkle root M, which is this big top node over here. He also gives some selected nodes, the hash of transaction 4, the combined hash of the first and second transaction, and so on and so forth. Now, you might be wondering, why of all nodes, why is he giving these 4 particular nodes? I think it's not very clear and explicit at this point in time as to why Flip is giving these 4 particular nodes. But in the next slide, you will see why is this so. So I've circled the nodes that Flip has given Jeremy. So for instance, the hash of the 4th transaction, the combined hash of transaction 1 and transaction 2, and so on and so forth. So as you can see, there are 4 circles on the Merkle tree. And now let's remove all of the nodes that we don't need. So now we're only left with nodes that Flip has given us. Now let's put 3 into the Merkle tree. So this is the transaction that we wish to verify in the first place. Now with the hash of the 4th transaction, what we can do is we can compute the combined hash of the 3rd and 4th transaction. And because Flip has also given us the combined hash of transaction 1 and transaction 2, we can again compute the combined hash of 1, 2, 3, 4. Okay, so same thing here, same thing here. So you notice how we can actually simply fill in the blanks to retrieve the Merkle root. And notice how we don't need any more information than required in order to compute the Merkle root. We only need the bare minimum. These 4 nodes are sufficient for us to compute the Merkle root. And now that we have retrieved the Merkle root, we can actually verify as to whether the Merkle root that is given to us by Flip and the Merkle root that we have actually computed, if they are actually equal. And if they are equal, it means that our transaction has actually followed through to the blockchain. Now, let's talk about cost savings. We can actually translate the cost savings mathematically. So in our case of 10 transactions, we only needed the Merkle root and 4 intermediate nodes, which are the ones that were circled previously. So the cost savings for this, for the case of 10 transactions, might not be very obvious. But if we were to extend this scenario to 500 transactions, instead of querying for 500 nodes, Flip, the blockchain node, can simply fetch M and 8 to 9 intermediate nodes, which is a huge improvement. Now, if we were to extrapolate this scenario to 5,000 transactions, Flip can simply fetch M and around 12 to 13 intermediate nodes. Just think about the improvement from 5,000 transactions to 12 to 13 intermediate nodes. That's all you need to retrieve the Merkle root. That's all you need for one to verify whether his transaction has actually followed through on the blockchain network. So in the future, I might produce a tutorial video on Merkle Trees, and I might also produce a working implementation with explanation of the Merkle Trees in either C++ or Python. Yeah, thank you.